right, my little beautiful yellow butterflies, let's jump into problem 2. So the question asks us to write the explicit equation for the pattern of squares in these shirt designs. Now, as you're listening to me, you might want to have the notes that I shared with you, like kind of to refer to, because I'm not going to be doing a whole lot of writing in this video here, okay? I just kind of want to talk you through the notes and what we're seeing. Okay, so the question asks us to write the explicit equation for the pattern. We're looking for patterns of squares in t-shirt designs or shirt designs. So remember, an explicit equation is just a math rule, it's just a little rule that lets you plug in any figure, like 1, 2, or even 100, or whatever number you want, whatever figure number you want to know, and you could have, 1002. Okay, what would be the number of squares for figure 1002? That's what explicit equations are designed to do. Okay, so that you can find the number of squares without building the design or listing every step. So we're thinking of the explicit equation of kind of what we're using when ain't nobody got time to figure out to do all that calculating when you have a figure number that is further down in the table that you're looking for. Okay, so let's look at the pattern again. So we're going to look at our loveliness here, our table, and we're trying to write a rule for f of x that tells us how many squares there are in figure x. Now, we have a couple of options. We can use the quadratic function. This way works every time, but I got a lot of pushback on this one. The students are saying, I don't want to use the quadratic function or the standard quadratic function because it's just way too much. You're doing too much, Miss Avery. Okay, so let's look at how we can do the quote unquote harder way, which is just kind of more steps, and a simpler way. All right, the simpler way is what we were using to start off with when we started the unit, when we were like really looking closely at the patterns and trying to find relationships and kind of making the numbers work, seeing what's happening from each place in our table. And the quadratic formula is just kind of that safety net that we wanted. Like if we are looking at these images and the tables and, what needs to be coming to us isn't coming to us, how do we get the explicit function? You can always turn to your friendly neighborhood quadratic function to do that, the standard function, okay? So briefly, to do that, you are going to brush this little baby off right here. That's what you're going to use. You're going to plug the values from the table, get 3 of those because you have to find A, B, and C. So you're going to get 3 of these values and plug them into this function right here. Then you're going to have to solve for systems of equations to find A, B, and C. And yeah, that is super intense, but it works, okay? So you are definitely free to use that method. Now, if you want to avoid doing all of that calculating, then you can go back to your design and we're going to take a really good look at what is happening here. So if you look at your figures, you'll notice certain patterns. Like here, we wrote out how many squares there are for each figure number. We see that we are increasing by, like this is +4, +6, +8. So there's a difference of 2 between each one of those. That difference is what's letting us know this is quadratic because it is growing in 2 directions here. Okay, it's getting taller and wider. And we noticed here, we talked about this beautifulness in class. We see here these squares that are squaring for us. So let's look at, for example, figure 3, okay? See what's happening here. We are adding a row and adding a column. And surprise, surprise, That's 3. It matches up with our figure number. Here we have figure 4. We're adding a row and we are adding a column. Okay, so we can describe this design as a growing corner, right? That is like n times n, or x being your figure number. Okay, if we multiply this by itself, 2 times 2, we get 4. 3 times 3 is 9. 4 times 4 is 16. Okay, and to that we have an extra row of squares that match our figure number. So that's going to be x. Okay, an extra row of x squares along the top. So that's plus 2, plus 3, and plus 4. Okay, so so this looks like this formula right here. I am seeing f of x equals n squared, right? N squared, going back up. So this is n. I square it. 2 times 2 gives me 4. N squared is 3 times 3, so that's 9. And that gives me this square right here, that 9. And if I square this x, which is my figure number, by itself, that gives me this. This is a 4 by 4. Okay, so that's what I mean by n squared. And then I'm going to add n to that. Okay, and what? See, I'm doing it again. Let me make this an x, because I have f of x here. So does it? There we go. All right. Pick a variable and stick with it, right? All right, so we have f of x equals x squared plus x. And I'm doing this plus x because of this right here, right? X, this is x. The figure number is x. X. And I am adding that x value each time. Okay, so I have plus x. So f of x equals x squared plus x. This is going to be your explicit function. Okay, and you can plug in some values there and it will check out. All right, so what does each part of f of x equals x squared plus x mean? Well, n squared is going to, x squared is going to be the main block of this shirt, okay? It grows like a square corner, n rows and x rows and x columns, okay? It is growing. Then we have plus n. This is that little extra horizontal row right here, okay? That little extra part. So that is our plus n. So when you're looking at the design, each figure grows both downward and to the side. The squares added, so it grows downward and to the side, downward to the side. So it is growing this way and it is growing that way. All right, the squares added to the top match the figure number. That's where the plus x comes from. So how can you figure this out on a test, right? You're not gonna panic. You don't have to use fancy equations if you don't want to, but it's there, if you need to be sure. But you're going to start by looking at the shape, see how it grows. Ask yourself, is this design forming a square, a staircase, a line? Count the parts. You can break down the square section, the top row, diagonal extras, break everything down and count your squares, and then try writing a rule in words first. Like for this example, it's a square plus a row, right? So we have a square plus a row, square plus a row, square plus a row. And that turns into math. We translate that into math speak and we get n squared plus n. All right, and that ends up being our final explicit equation. So, all right, now let's move on to writing the recursive equation. This one is different. Instead of jumping straight to figure 100, a recursive rule tells you here's how to get the figure if you already know the current one, all right? So let's look at this table again. And do we see a pattern here? The number of squares increases by 4, then 6, then 8. So this is not constant, but wait, there is a pattern here. The amount added each time is increasing by 2. So plus 2 plus 2. Right? The number added is always 2 in this figure. So look, from figure 1 to figure 2, we multiply 2 by 2. So we're adding 2 by 2 from figure 1 to figure 2, all right? From figure 1 to figure 2, we're adding 2 times 2. From figure 2 to figure 3, we add 2 times 3 equals 6. From figure 3 to 4, we add 2 times 4 equals 8. So what's the recursive rule here? We're going to write the recursive rule, like our starting value, okay? F of, let's get this written down. All right, our starting value, I'm just going to do this first because we always have to include that, okay, equals 2. Starting value. And then we're going to have f of x equals f times our previous, okay? And we're going to add to that 2 times n. So what does each part mean in context of the shirt design? Well, our f of 1 equals 2. That's the very first shirt design. It has 2 squares. This right here, this takes the shirt from the step before, all right? So that's our previous shirt. And then plus 2, you're adding 2 extra rows of x squares. So one going across the top and then one going down the side, all right? But remember, there's one shared square, so it kind of simplifies to plus n on each side, which is 2n total. All right, so how do I know it's 2n? Well, you are going to look at how many squares are added between each figure, okay? And now look at the figure number you're going to. So figure number 2, we are adding 4. For figure number 3, we are adding 6. For figure number 4, we're adding 8. Ask yourself, can I multiply the figure number by something to get that change? Well, yeah, so 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8. So, yep, absolutely, it's 2 times n. So that's how you spot 2n in the recursive pattern. So your final recursive rule is right here. And just to kind of summarize, for your explicit, you're going to, that means that you're plugging in any figure number to get squares. And we know our rule was f of x equals x squared plus 2. Then for recursive, that rule means that we are, that you build the next design using the last one, okay? And this is our recursive right here, okay? So I need to stop there because students are banging on my door trying to get in. But I hope this is helpful and get you prepared to answer questions 2 and 3 on your test.